understanding of the universe seems to be fundamentally flawed. Cosmology, the study of the universe's origins and structure, is grappling with a critical conflict. How fast is the universe expanding? For over a decade, two distinct methods of measurement have yielded contradictory results. Observations of the current universe often show the expansion rate, known as the Hubble constant, to be approximately 9% faster than predictions based on data from the early universe. Scientists hoped the advanced capabilities of the James Webb Space Telescope, JWST, would resolve this discrepancy. Instead, its exceptionally precise observations have reinforced the inconsistency, challenging the standard cosmological model. This has sparked debates about the need for new physics to either modify or replace the 40-year-old lambda cold dark matter, lambda CDM, model. The expanding universe and the Big Bang theory. The universe's story begins with the Big Bang, a cataclysmic event where energy, mass, and space burst into existence in an instant. In its infancy, the universe was a searing plasma of matter and antimatter particles annihilating each other on contact. However, an unknown asymmetry caused slightly more matter than antimatter to exist, allowing the universe to survive and evolve. As gravity compressed the plasma, sound waves called baryon acoustic oscillations rippled through the matter, moving at about half the speed of light. Meanwhile, the universe expanded rapidly, with clumps of matter forming the seeds of galaxies. Over billions of years, ordinary matter coalesced around dark matter, an invisible substance, creating the vast cosmic web of interconnected galaxies. Around 5 billion years ago, something unexpected happened. The universe's expansion began accelerating, driven by a mysterious force called dark energy. Dark energy, possibly a cosmological constant, is an unchanging property woven into the fabric of spacetime. It now dominates the universe, accounting for about 70% of its energy density. The lambda CDM model and the Hubble tension. The lambda CDM model has been remarkably successful in explaining the universe's evolution, predicting its ultimate fate as a heat death, where matter is dispersed so widely that no significant interactions can occur. According to the model, the universe's composition is 5% ordinary matter, 25% dark matter, and 70% dark energy. Yet, we don't fully understand the nature of dark matter or dark energy. More troubling is the Hubble tension, a significant disagreement between two methods of measuring the universe's expansion rate. Observations of the cosmic microwave background, CMB, the afterglow of the Big Bang, indicate a Hubble constant of around 67 km per second per megaparsec, km/a/mpc. In contrast, measurements based on more recent cosmic phenomena like pulsating stars suggest a value closer to 73 km per second per mpc. This discrepancy has persisted despite rigorous scrutiny of both methods. Measuring the universe's expansion. 1. Cosmic microwave background, CMB. The CMB is the oldest light in the universe, emitted 380,000 years after the Big Bang when the universe cooled enough for atoms to form. This relic radiation provides a snapshot of the early universe's density and structure. By analyzing variations in the CMB, scientists derive key parameters for the lambda CDM model, including the Hubble constant. Data from the European Space Agency's Planck satellite placed the value at 67 km per second per mpc with less than 1% uncertainty. 2. Cepheid variable stars. Cepheid variable stars are pulsating stars whose brightness fluctuates in a predictable pattern. Discovered in 1912 by Henrietta Swan Leavitt, their pulsation period correlates with their intrinsic brightness, making them reliable standard candles for measuring cosmic distances. Observations of these stars in nearby galaxies yield a Hubble constant of approximately 73 km per second per mpc. The role of the James Webb Space Telescope. The James Webb Space Telescope, designed to probe the universe's earliest light and most distant galaxies, was expected to bridge the gap between these conflicting measurements. Instead, its observations have amplified the discrepancy, suggesting the lambda CDM model might be incomplete. Adam Rees, a Nobel Prize-winning astrophysicist, notes that the disagreement could point to something missing in our understanding of the universe. This missing link might involve new physics beyond the lambda-CDM framework. For instance, some researchers speculate that additional components like unknown particles or forces might be influencing the universe's expansion. A new era of cosmology. The tension between these measurements could signal the need for a paradigm shift in cosmology. If dark matter or dark energy behaves differently than previously thought, or if a new form of energy exists, it could reshape our understanding of the universe. The JWST's groundbreaking ultra-deep field images and its ability to observe faint, distant objects with unparalleled clarity have provided critical data. These observations challenge existing models and offer tantalizing clues about the universe's true nature. As scientists continue to analyze its findings, the possibility of a fundamental breakthrough looms. Conclusion: the universe's expansion is one of the most profound mysteries in science. The conflicting measurements of the Hubble constant have exposed cracks in our cosmological model, prompting scientists to question long-held assumptions. The James Webb Space Telescope, instead of resolving the issue, has deepened the enigma, suggesting that the universe may hold secrets yet to be uncovered. As research advances, we may discover that the universe is far more complex than we ever imagined. Whether through new particles, forces, or entirely novel physics, the answers to these questions promise to revolutionize our understanding of the cosmos. The James Webb Space Telescope, JWST, is revolutionizing our understanding of the cosmos, addressing some of the most profound mysteries in modern astronomy. Among these are the enigmatic phenomena of dark energy and dark matter. While some theories suggest the possibility of multiple types of dark energy or interactions between dark matter and light, these hypotheses add complexity to cosmological models, requiring further evidence before being widely accepted. When launched, JWST was tasked with peering farther back in time than any telescope before it, capturing light from galaxies formed just 300 million years after the Big Bang. However, its observations have revealed early galaxies that are significantly more massive and evolved than predicted by the standard cosmological model. According to the prevailing theory, these primordial galaxies should have been dominated by young, hot stars forming at a frenetic pace. Instead, JWST discovered that many were rich in heavy elements from earlier stellar generations and already harboring massive central black holes. These findings have sparked intense debate, suggesting that processes driving galaxy formation and evolution in the early universe were faster and more efficient than previously thought. This discrepancy between theoretical predictions and JWST's observations challenges the standard model of cosmology. Resolving issues like the Hubble tension, disagreements over the universe's expansion rate, and understanding the unexpected complexity of early galaxies may require either new physics or significant adjustments to existing theories. This pursuit represents one of the most exciting frontiers in modern astronomy. JWST's groundbreaking infrared imaging capabilities allow it to see farther and more clearly into the universe than ever before, capturing light from some of the earliest galaxies. These observations contradict the notion that early galaxies were simple, immature structures. Instead, JWST has shown that these galaxies were surprisingly mature, containing heavy elements and hosting supermassive black holes at their cores. Such findings raise important questions about the mechanisms driving galaxy formation shortly after the Big Bang. Additionally, JWST's discoveries have intensified the ongoing puzzle surrounding dark matter and dark energy, which collectively comprise most of the universe's mass-energy content. Dark matter, which interacts gravitationally but not electromagnetically, plays a critical role in shaping the large-scale structure of the universe. Despite extensive efforts to detect and understand it, the nature and composition of dark matter remain elusive. Meanwhile, dark energy, the mysterious force driving the accelerated expansion of the universe, presents an even greater challenge. While the standard model suggests dark energy is a cosmological constant with uniform properties, phenomena like the Hubble tension hint that its behavior might vary over time, suggesting dynamic forms of dark energy. These revelations prompt researchers to explore alternative theories, including modified gravity, exotic particles, and interactions beyond the standard model of particle physics. Beyond cosmology, JWST is reshaping broader astrophysical inquiries, such as the conditions necessary for life-supporting planets and the emergence of complex chemistry in the universe. By studying distant galaxies and their environments, astronomers hope to gain insights into how Earth-like planets form and evolve around stars, shedding light on the prevalence and diversity of life in the cosmos. Looking ahead, JWST promises to continue pushing the boundaries of our cosmic knowledge. Its unparalleled sensitivity and resolution will allow scientists to study the atmospheres of exoplanets, characterize distant galaxies in extraordinary detail, and probe the earliest epochs of cosmic history with unprecedented precision. These endeavors not only enhance our understanding of the universe's past but also pave the way for transformative discoveries that could redefine our understanding of physics, astronomy, and humanity's place in the cosmos. As JWST enters its operational phase, astronomers eagerly anticipate its contributions to unraveling the universe's most profound mysteries. From exploring the nature of dark matter and dark energy to investigating galaxy formation and searching for life beyond Earth, JWST is poised to revolutionize our comprehension of the cosmos in ways once thought impossible. This fusion of advanced technology, theoretical innovation, and meticulous observation heralds an exciting era in cosmology and astrophysics. By offering a clearer view of the universe's earliest moments, JWST is set to challenge and refine fundamental theories about its structure and evolution. As we embark on this journey of discovery, the telescope stands at the forefront, ready to unveil the secrets of our cosmic origins and destiny. The discovery of Cepheid variables as standard candles revolutionized our understanding of the universe, enabling astronomers to measure the absolute brightness of stars and, consequently, their distances. This milestone revelation transformed Cepheids into reliable tools for gauging the vastness of the cosmos. By analyzing the pulsations of these stars, scientists constructed cosmic distance ladders, with each step providing a window into the universe's history. This method remains one of the most precise tools available for measuring astronomical distances. To build this distance ladder, astronomers start by selecting nearby Cepheids and cross-referencing their distances using pulsating light measurements alongside geometric methods. Astrophysicist Wendy Friedman of the University of Chicago explains that subsequent rungs rely on Cepheid data alone. From there, researchers examine the distances of stars and supernovae on each level and compare their redshift, the stretching of light to longer, redder wavelengths caused by the universe's expansion. This process yields precise measurements of the Hubble constant. In 2019, Adam Rees and his team used this approach with the Hubble Space Telescope to observe Cepheids in the Large Magellanic Cloud, a close neighbor of the Milky Way. Their findings were striking, suggesting an expansion rate of 74 kilometers per second per megaparsec, a value higher than those derived from cosmic microwave background (CMB) measurements. However, Hubble's limitations, particularly in densely packed regions of space, left room for debate. Skeptics argued that measurement errors could have influenced the results. When the James Webb Space Telescope launched in December 2021, it promised to address this disparity. With its 6.5-meter wide mirror, 3 times the diameter of Hubble's, Webb could observe fainter objects and detect a broader range of infrared wavelengths. The telescope's capabilities allowed astronomers to compare Cepheids in galaxy NGC 4258 with Type Ia supernovae, another standard candle due to their consistent peak luminosities. Remarkably, the results closely aligned with Hubble's earlier measurements, yielding a value of 73 kilometers per second per megaparsec. Additional methods, such as observing the brightest tips of red giant stars or light distorted by massive galaxies' gravitational fields, produce similar values of 69.6 and 66.6 kilometers per second per megaparsec, respectively. Despite the converging evidence, the persistent discrepancy, known as the Hubble tension, left cosmologists puzzled. The difference between the early universe measurements, CMB, and the local universe values suggested that this wasn't a mere statistical anomaly. Rongrong Kai, a cosmologist at the University of California, Merced, emphasized that the data strongly pointed to the need for new physics, as a random chance was unlikely to account for the 7 kilometers per second difference. This unresolved tension has split the cosmological community, with researchers debating between measurement errors and potential breakthroughs in physics. At a 2019 conference at the Kavli Institute for Theoretical Physics, attempts to resolve the conflict only deepened the divide. As the late Vera Rubin, who discovered evidence for dark matter, once noted, scientists often become deeply attached to their interpretations, making consensus elusive. By February 2023, further results from James Webb and updated Hubble distance ladder measurements confirmed the Hubble tension, leaving the field with three primary explanations: measurement errors, new physics, or a combination of both. Kai noted that most data supports new physics, with one popular hypothesis being that dark energy behaves differently now than it did in the early universe. If dark energy were stronger in the past and later diminished, it could make the early universe appear smaller, causing today's expansion rate to seem faster. Alternative theories abound, but the mystery remains unsolved. For now, the tension between early and late universe measurements continues to challenge our understanding of cosmology, driving researchers to probe deeper into the underlying forces shaping the cosmos.